Hello, I'm David. I'm the coordinator of the Maths Learning Centre at Uni of Adelaide. It's semester 2, 2023, and this is a revision seminar for Maths1A. We've had a bit of a chat about what we might talk about, and I've chosen upper and lower sums as the beginning thing to talk about. So here we are. So if you agree that upper and lower sums is a thing that is on your mind, what sorts of questions have you got about it? Okay. Anyone want to add anything? Okay. Anything else? What's that? Is it going to be in the exam is a question that I cannot answer. I am not one of the people who makes the decisions of what's in the exam. The Maths Learning Centre isn't part of the School of Computer and Math Sciences. I belong to the whole uni, so I don't know. All right, here's some good questions. Just make sure I will deal with those things. So the answer is there a step-by-step process? Is yes, sort of. There's some big steps. So there's some sections of steps. So it just might be easier to run through an example, hey? But just wait. Before I do, I don't think I've ever done this in a revision seminar, so I think I just want to do this. The idea of upper and lower sums is based on this idea. There are two ideas going on here. And it might take me a little while maybe 5 minutes to sort this out. So this is an idea. The idea is this. Here's a graph. It's horizontal. And it's, just as an example, the idea is this. The area of the integral of this function, like the integral of this function from 2 to 5, this is f of x here, is, 3 times 6, 18. It's a rectangle. That's great. Okay, so we've got 3 times 6 is 18. That is the first idea, that I can calculate the areas of rectangles. If they are 3 wide and 6 high, then the area is 3 times 6. Great. So if I have a function that's made entirely of flat bits like this, then I just need to know how wide each flat bit is and just add up all the little rectangles. That's idea number 2. A second idea this function, which is a straight line, it's my f of x this time. It goes from 4 to 8 as it goes from 2 to 5. This bit fits neatly in here. And so the area is still 3 times 6. So that number 6 that I've got there, just here in the middle, that's the average value of the function. Because it spends just as much time being below 6 as it does above 6. And for everyone that's like a little bit above 6, there's a matching number that's a little bit below 6. It's the average value. Right. Did they use the phrase average value in this course? Once? Okay. So it turns out that if you know what the average value of your function is on a particular zone, and you want to find the integral, you can just pretend it's a rectangle and it is flat at the average value. Cool. I don't know if that's useful at this time, but I think it was a useful thing to think about. Okay. Last thing. Cool, huh? Okay. Just make that a little lower. This function is not nearly so neat as the ones I've done so far. But if I could somehow average out these values to a horizontal line, then the area would be whatever that horizontal height is times this width. And I would have to, when I do that average, I would have to say, oh, well, it spends a lot of time being up here, and so it should be a little higher because of that. And you have to figure out what you mean by average value in that context. But I am certain that if there is an average value, it's got to be somewhere between the minimum and the maximum. So since I know that the area on this zone is going to be this rectangle, this green rectangle here, is going to be the same as the area of my shape. And I'm absolutely certain that that height is somewhere between here and here. That means that this area is going to be somewhere between this area and this area. That's the idea behind it. That's the entire concept that we're working on here. So whatever the integral from 2 to 5 of f of x dx actually is, it's going to be somewhere between 3 times whatever the maximum is and 3 times whatever the minimum is. Like that. Now, figuring out what that average value is tricky. But if I cut my function into small enough pieces, they would all look like this. If I zoom in far enough to any function, it looks straight. And so therefore, if I went in far enough, if I cut into enough pieces, I could just do the minimum maximum on every one of those zones, and it should be okay. That's the idea behind it. So if I do this on thin enough slices, I will get the answer I want. That is the idea of what this upper and lower sums is about. But you have to add up all the slices to get the total area. There is in fact nothing stopping you from choosing slices of different widths. But the thing that does stop you is it's just harder. So here we are. We now have an idea of what we're going to do. We're going to say that we're going to cut my interval into thin enough slices, which means cutting it into as many slices as we need. We're going to figure out this idea of being somewhere between the minimum and the maximum on every one of them. And I'm going to add up all of those answers, and we'll get a grand minimum and a grand maximum, and they are going to be what my integral has to be between. That's the idea. So here we go. Steps. You ask for steps, here they are. The steps are these. Step 1. Divide the interval into n equal subintervals. There are several things you need to know about your subinterval in order to do the rest of the steps. And so step 1 has a few steps. I'm sorry. You need to figure out how wide those subintervals are. And you need to figure out where they start and where they end. I have some people who I've done this to live in the Maths Learning Centre nodding along the way. The width of each I need, which most people call delta x. And I need to know the right-hand end of each, which most people call xi. And I need to know the left-hand end of each, most people call xi minus 1. And here's a picture of it. There's your big interval, which goes from like A to B, and you cut it into all these pieces. And this width here is delta x. And this right-hand end is called xi. And this left-hand end is called xi minus 1, where the I stands for interval. It actually stands for index, but it makes more sense to me to call it interval. The I stands for which interval I am up to. So this thing here is subinterval number I. So subinterval number 1 is delta x wide, and it finishes at x1 and starts at x0. And subinterval number 10 is delta x wide, and it finishes at x10 and starts at x9. And subinterval number 20 finishes at x20 and starts at x19. In fact, I may just write down what I just said. So e.g. subinterval number 5, for example, ends at x5 and starts at x4. That's the idea. Okay, and every subinterval does that. And if you're very paying close attention, x0 is the beginning of subinterval number 1 and is therefore A. And xn is the end of subinterval number n, which is the last interval and is therefore B. Just in case you were wondering about that. So just to say, x0 is the left-hand end of the first interval, and therefore it's B, it's A, sorry. And xn is the right-hand end of the last interval, and therefore it's equal to B. There you go. One of those things. If you do a course in the future called with numerical methods in the title, this will come back, this concept of x0 and xn being the beginning and the end. Okay, that's step 1. And step 1 always looks the same, completely regardless of what the function is. It is based entirely on the interval itself. You don't need to know the function for this part of the process. So I have one question, which I know the answer to, which is bad practice as a teacher, but how do you figure out what delta x is? So you divide this total length by how many subintervals there are, because that is exactly what division is for cutting things into pieces. And so just while we're at it, I might work on this here. This is the total width, B minus A, divided by the number of pieces you cut it into. please don't remember it as b minus a over n. It's the total width. Like, so with this one, I don't even have to calculate 5 minus 2. I know what that is. It's 3. So just, you don't have to show the calculation b minus a. You're allowed to just put the total width there. Yeah. But also, you don't have to think about that calculation either. It's the total width divided by how many pieces you cut it into. Okay, that is step 1. Always the same, except, oh crap. How do you figure out what xi is? You are right that I will have to eventually draw a graph to see whether it's increasing or decreasing, but I don't have to do that to figure out what this position on the x-axis is. Yep.
It's x0 plus the amount of across.
That's an excellent way to describe it. I'm so excited that you said it exactly that way. Xi is reached by going I lots of delta x from the beginning. It's just to get to the end of the first interval, I have to start at A and go 1 lot of delta x. And to get to the end of the second interval, I have to get to the end of 2 lots of delta x. And to get to the end of the ith interval, I have to get to the end of I lots of delta x. So the way that you described that was great. It was like, well, the number of steps you've taken to get to the end of interval number I is, in fact, I. So this entire process can be done perfectly well without any of the function itself. You don't need to know whether the function's increasing or decreasing. This is just telling someone what all these marks on the x-axis actually are and how to figure out what they are. And xi minus 1 is the previous, is 1 step back from there. Yay. Okay, the rest of this I'm going to just say generally, and we'll do the rest of it in the example. So step 2. So that was step 1, and there are 3 pieces to step 1. Step 2 is, now you have to look at every individual interval and decide what the maximum and what the minimum is on that interval. Maximum on interval subinterval number I, and the minimum on subinterval number I. And this is called capital MI, and this is called little mi. And as you described, you definitely need, is that better? Here we are on interval number I. Wow, crap. Second. And you need to know what your function looks like on this interval to know where the maximum is and where the minimum is. If you are unlucky, they'll be somewhere in the middle. And if you have specifically 6 intervals, not n, but 6, you can actually look at your function and go, oh, yep, that one's in the middle. I'll just have to calculate the middle one. But if you are doing it with n and you don't know what n is, that's too tricky. And so they will, in this course, always give you functions that are either increasing or decreasing, and the decision of which end it is always the same decision. Because they don't really care about you being able to do this. They care about you knowing what this is and being able to manipulate sum notation. The main purpose of this being here is for you to have practice fiddling with sum notation, because it's a skill that you probably will need if you go on to more mathematics after this. So, so it's either this or this probably, one of those. So on this one, the minimum is at the right-hand side and is the function value on xi. And the maximum is at the left-hand side and is the function value on xi minus 1. But in this one, the minimum is on the left-hand side. So mi is the minimum is f of xi minus 1. And capital Mi is f of xi. So I'm going to say something. This is not mi minus 1. This is mi. The I is saying belonging to this entire interval. And when I look at that whole interval and find where the minimum is, it's over here on the left-hand side. So you have to make that decision. All right. And so you will have a formula, capital Mi is equal to f of xi or f of xi minus 1, depending on which way the function goes. And then the third step is to figure out one of these two upper and lower sums. And then you'll figure out the other one. That's step 4. So step 3 is pick whichever of them is at the right-hand end, which is the easiest one, and calculate that one. So now, to be fair, if it felt easier to calculate the one at the left-hand end, go for it. Totally up to you. But my advice is that you should use whichever of them is at the right-hand end, because it will be easier, because it will have i's instead of I minus 1s. And all those minus 1s is just begging for you to lose minus signs along the way. There is, and we will get to that. And this will use sum notation. And you will have to use various sum notation things. And then step 4 is to find the other one. And step 5 is to write down the integral. Like you've got to do a limit or something. Step 5 is do the limit. Okay. That is how the process works. So it is useful to be able to, on any example that you see, to find which bit of it is each of those parts. And I recommend drawing boxes around each part and go, this is the bit where they figured out what the intervals were. This is the bit where they figured out what the maximum and the minimum is. This is the bit where they figured out what UN is, and that sort of thing. Now, we all know that it's possible to calculate this area without using upper and lower sums, using the magic of calculus. But one of the purposes of upper and lower sums is to make you appreciate the magic of calculus as well. So here we are. So step 1, divide the interval from -1 to 3 into n equal subintervals. And if you are showing this working, you should write that sentence so that the person reading it knows what you are doing. Also, in your exam, it is extremely unlikely, based on past experience, for them to get you to do an entire one of these. They might, it's too much work for the, 2.5 hours, I think it is. Too much work for the 2.5 hours you're working on. So they're much more, don't what? Oh, my lights have changed. It's coming back on again, so it's just... All right, that was fun. Okay. I just want to point that out. If they mention upper and lower sums, don't launch into this entire process and do all of it. Stop for a minute, read what they've asked you to do, and decide if they've done part of it for you. And decide if you have to do all of it. At least once in past years, they've said, write the upper sum using sum notation, but do not calculate. Yep. And at least once they've said, here is a formula for the upper sum. What is the lower sum? Okay, just be aware that it's very common for long things for them to only ask part of it, or for ask you how the bits are connected. So just make sure you don't just launch into the process. So just because there are steps doesn't mean you have to do all of them today. Okay. All right, so we divided into n equal subintervals. The width of each is delta x, which is now, how wide is this? This is 4 wide. Goes from -1 to 0, that'll be 1, and then 1 to 3, that'll be 4, divided by n. And the right-hand end of subinterval number I is called xi, and it is the extreme left-hand end -1 plus I lots of delta x, which is -1 plus I lots of 4 on n. And the left-hand end of subinterval number I is xi minus 1, which is -1 plus I minus 1 times 4 on n. That is step 1. Didn't take very long when we actually did it in practice. Took a while to describe, but that's the entire step 1. The next step is to find the maximum and minimum on each interval. Yeah. So you don't necessarily have to put a heading for what you're doing there. But you do have to decide where the maximum minimum is. Oh, whoa, just a second. I might change my function. Just one moment. It's okay. The turning point of that function is at -1. So that's not inside the interval. It's all good. So I'm going to do a quick sketch of this function. I'm actually going to explicitly say that f of x is equal to this function. Officially, nobody has mentioned f of x yet, so you're supposed to tell them what f of x is. The person reading your exam is probably not going to care that much, but it's good practice if they haven't mentioned what the thing is to tell them what it is. And I just need to sketch this, and I notice that this does this, and so that function has that is the wrong thing. I'm going to make that a plus, if that's okay. Thank you for letting me change the question on the fly. You can't do that in the exam, I'm sorry. But I will say one thing. If you keep coming back to a question and skipping it, and you've got like 20 minutes to go, and you can't figure out how to do the question they actually asked you to do, not the worst thing to just say, this is a similar question, I'll do that one instead. Well, because then if you say something useful, and it makes the difference between passing and failing, they'll give you a mark. So that's just, that is an extreme worst case scenario situation. But it's a little bit like, you know, when they've got a part A, part B, part C, and you can't do part B, but you need the answer to part B to do part C. Well, just say, assuming the answer to part C is 5, part B is 5, and then run and do part C. And that's okay. So just want to point that out. It's a useful thing to do. Yeah, because they will give you marks based on the working you do. And
it's possible to get full marks if you assume part,
well, yes, it's possible to get full marks for part C if you assume the answer to part B, except if you happen to choose an answer that makes it much, much easier than it would have been otherwise. So, oh, yeah. You get follow-through marks, yeah. That's how they've always done it before. I don't know if they're changing it, but I wouldn't have expected them to. The people in the School of Maths and Computer Science are nice sorts of people. They wouldn't do that to you. So just worth pointing that out. I should also warn you that sometimes the part A, part B, and part C aren't related. But usually they are. But I've seen past exams where they're not, where someone came to me and said, oh, they said part A, part B, part C, and they just weren't related at all. Yeah. It's only because they give different questions to different people. Anyway, this has zeros at 0 and -2, like that. And, well, you know, x equals 0 makes it 0, and x equals -2 makes that 0. And it's a parabola, which means the turning point's at -1 halfway between. And so the zone I'm looking at here, which is from -1 to 3, it's increasing on that zone. Another thing to warn you about is that your lecturers will always assume you can do any reasoning that might have been in any part of high school, including being able to tell what shape that graph is. So just thought I'd stick it in there. Okay. If they're very nice to you, they'll give you a linear function. It's much easier to tell. So f is increasing on this interval . So the maximum on interval number I, on subinterval number y, is at the right-hand end. Because it's increasing. It's always going up. The maximum is at the right-hand end. And so therefore, capital MI is the function enacted upon the right-hand end. So this symbol, this statement here in symbols is pretty much the same as what that statement is there. And the minimum on interval number I is at the left-hand end. And so therefore little mi is f of xi minus 1. Cool. So I have now figured out where the interval, the maximum minimum is. I'm going to only figure out the actual function value for this one. So capital MI is f of xi, which is x squared, so -1 plus I 4 on n, that's what xi is, squared, plus 2 times that's the function value, which sucks royally, but there we go. We can cope. -1 squared plus 2 times -1 times I times 4 on n plus that squared -2 plus I times 8 on n. Yeah. Got a 1 minus 2, so that's -1. We've got minus 8i on n and a plus 8i on n. They cancel each other out. Nice. I did not expect that to happen at all. I reckon the reason that's happened is because it's the turning point's right at the edge. Okay, cool. And all right. Okay, so now we're going to find the upper sum. The formula for UN, which I should have put back here on this previous page. Well, just think about how it works. Every interval, the maximum, I'm going to need to use that as a rectangle and times it by the width. And so I'm going to have the delta x times the maximum on that interval. And I'm going to add up all of those different answers across all of the intervals. This is easier for me to remember because of the shape of the picture that's going on. It's delta x wide and it's mi high, and so that's the idea behind it. And I can always pull the delta x out the front because it doesn't have an I in it. And capital MI is this. Damn it. Can I please put a line of working in between this? It's very important that I do this line of working. Or later. I'm going to put that in. There's nothing stopping you doing this working here, except nobody wants to write sum signs 15 times. So, what was that? You can. So now, here we are in the bit where we have to use the sum notation. So if they said to you, I guess the delta x is 4 on n, which I can put in later as well. If someone said to you, write down an expression for un using sum notation, this would be the answer and you would stop. Because this is a perfectly good expression. It used sum notation. I'm just going to stop. But you would still have to do all that previous working to set it up. This is an expression for un using sum notation. And it's not like that's actually what the name of it is. This is just an ordinary description of what this is. If someone had to ask me, what is this? Okay, well, it's an expression for un because everything's an expression and uses sum notation. So, yeah. Okay. It's good to think about these things before you get to an exam. So when all of your other stuff that you do in this course when you're studying, think about the kinds of ways they might ask you questions. What sorts of sentences might they say? And so that you can be pre-prepared to answer them. Yeah. So now we are up to using sum notation. So the delta x was 4 on n. And then you suggested that one of the rules of how sum notation works is that I can apply it to two pieces that are added separately. So I can add the minus ones, and I can add up all these minus ones, and I can add up all of these separately, and it'll come to the same answer. I'm going to show that line explicitly. You do not have to show this line if you do not want, but I'm just going to make sure that I do. The other thing you can do is anything that doesn't involve an I that's multiplied on, you can factorize it out. So most people who are familiar with this process will do this step from here to here in one go. They won't write the middle line. They'll say, oh, I can bring this sum in across the plus, and then I can bring this 16 and n squared out, and they do it all in one go. But it's okay not to do it all in one go if you feel like you'll get it wrong if you don't. Here we go. So now we have to know some things about sum notations. So far, the things about sum notation that we've used are facts about how it sort of interacts with plus and times, like the manipulation rules. But now we need to know some formulas. So if we add up n lots of minus 1, it will be n lots of minus 1. And there is a formula for the sum from 1 to n of I squared. There are two formulas for it. One of them is factorized and the other one's expanded out. And I can't remember the factorized version off the top of my head, but I can remember the expanded out version. This. Oh, this could be 1/6 of n plus 1 2n plus 1, I think. I thought I couldn't remember it, but there you go, I can. Well, they're differently useful in different situations. And some people find this one a little easier to remember. I find this because it's 3, 3, 2, 2, and then that 6 is 3 times 2. It's lovely. It's neatly expanded out for you. I'm very glad that my Maths1A lecturer gave us both. Yeah. Okay, and now the sums are gone. This is a perfectly good ordinary algebra problem now. I want to go as far as I can. So here we go. I can expand this out now. So I've got 16 on 3n, because that n squared cancels. No, there's an n on the top. 16n on 3. The n squared cancels with 2 of those n's. I'll get 16 on n squared on 2, so I'll get 8 for that one. And now I'm going to get 16 on whatever 6n is. And I'm sure I could cancel some of them out, but I don't feel like it at this time. We are doing very well. And we have 16 on 3 minus 1n, which would be 13 on 3n. And now we'll expand this out, and we're going to have 4 times 13. I know what that is. That's 52. Oh, crap ass. This one's we don't have an n because that n cancels that n. And this one's an n squared now. Is that what you're getting at? Thank you. And this is the format you want. You want plain number and stuff with n's on the bottom. That's the goal. So at this point, I know that the actual value for the integral will be 52 on 3, as long as I've done all this working correctly. Because as n gets bigger and bigger and bigger, this bit will get smaller and smaller and smaller, and I'll end up with 52 on 3. If you've done this correctly, if you're doing the upper sum, these two bits should be positive together. It's just worth pointing it out. Because if you end up with these being negative when you join them together, then that can't be the upper sum, because it would be below the correct answer. So, yeah. So now we'll find the other one. How are we feeling about what's happening here? Yep. Specifically want to ask people who asked for this in the first place. Now, of course, this will be much faster if you were doing it in an exam because you won't be explaining to the person in front of you what you were doing. Okay, so, okay. Ready. Ln is the sum from I equals 1 to n of delta x times little mi. I'm just pointing out that if this function had been a decreasing function, I would have found ln first because it would have been the one with the xi and not the xi minus 1. And this is this. So if it helps you to make the decision, it's totally okay to write down both ln equals and un equals so that you can go, aha, this is the one with the I, I'll do that one. In fact, next time I do this, I'll try and remember to do that. Okay. Are you ready? That's un there. That's un there. And then that's ln there. And they are almost identical. And the only difference is this I and I minus 1. Interesting. And this function is decreasing. And so the maximum on one interval is the minimum on the next one. Like, sorry, the minimum on one interval is the maximum on the next one because it keeps going down. And so this, like, xi minus 1 is the xi from the previous one. And so these two sums involve mostly the same numbers. Just going to do one little change. If I sub I equals 1 into this, then the answer is 0. If I sub I equals 2, the answer is 1. If I sub I equals 3, the answer is 2. And so it's really the same as subbing 0 to n minus 1 into this formula. So subbing 1 to n into this formula is the same as subbing 0 to n minus 1 into this formula. And that's a sum notation move that you're allowed to make. You can add 1 here and subtract 1 here, and you compensate for the change that you've made. And so it all works out to the same answer. So the lecturer did it with like a j equals blah. It's a lot of people that makes a lot of sense to, and I'm really happy if you do it that way, but that just introduces extra letters and it just confuses me. So if it's easier for me to just think about what numbers are ending up in this spot and do that. This process in later years courses is called index shifting. The index is the number that tells you where you're up to in the sum. And it literally is index in the sense of your index finger. You are pointing to the correct spot. Index means point in Latin. So, in case you were wondering. And so index finger literally means in Latin pointer finger, which is what they call it on play school, the pointer finger. So there you go. Yay. Okay. It's amazing how many things are just Latin for an ordinary word. So anyway, here we are. Now when I compare them, they're even better. This is exactly the same list, but it uses different set of numbers as it was for big MI, right? But for capital M, UN. UN is from 1 to n of this thing, and ln is from 0 to n minus 1 of this thing. So just a second, we've got 0, 1, 2, all the way up to n minus 1 and n. ln uses these ones, and the un uses these ones. And so all the ones in the middle are the same. And so what I've got is, here's the magic trick. I know the answer for un. So if I remove the one with the I equals 0, then I'll have this bit. So this is what ln is, this bit here. If I remove the I equals 0, I'll have this bit. And if I put the I equals n in, I'll have that bit. So I'm going to remove the one where I equals 0. And go all the way. So now it looks like this. That's the one for 0, and I go from 1 to n minus 1 instead. And I'm going to go all the way up to n. And I'm going to have to take off the one for I equals n. Like that. So this thing here, just here, is the same thing as this thing here. There's more than one way of doing this working. In fact, I may have a better way of doing it. Oh, this is fun. Just wait. Can I do something? I have an alternative. So you can do it this way and get delta x times f of minus 1, because that's what x0 is, plus un minus delta x times f of 3, because that's what the other end is. And we know what this answer is. This is 4 on n times minus 1 squared. Was it plus 2 times minus 1? What's the original function? Yeah. And the un we just figured out, that's 52 on 3 plus 32 on n plus 64 on n squared. And f of 3 is 3 squared plus 2 times 3. Ta-da! All the sum notation's gone. And it's still going to be a 52 on 3 because everything else has an n on the bottom. So you could theoretically figure out what all this was. What's that? Minus 1. So maybe I should have kept un until later when I figured this out. I'm just going to put the un back. No, I'm committed now. 3 squared is 9. Is there a 6n squared on the bottom there? 6n squared? Oh, I did. Thank you. I forgot there's 6 here, yeah? Hold on. 9 plus 6 is 15. Look at that. Are you ready? Ready? Minus 1 lots of 4 on n and minus 15 lots of 4 on n is minus 16 lots of 4 on n, which is minus 64 on n. And 32 minus 64 is minus 32. Yeah. Thank you. It did. It changed this to a minus. Not that one, just this one. In general, when you do upper and lower sums on a polynomial, the upper and lower sums will be the same, except that the term with the 1 on n will be minus in the lower sum and plus in the upper sum. Yeah, but it's not like they've given that to you as a theorem in the notes. So we have that the integral is between ln is less than or equal to -1, the integral from -1 to 3 of f of x dx, which is less than or equal to un for all n. That is the truth. The upper sum, all the upper sums are more than the integral, and all the lower sums are less than the integral. And the only number that is between both of those for all n's is 52 on 3. Because the limit of this thing that's more is 52 on 3, and the limit of this thing that's less is 52 on 3. And so this number is squeezed between those two. And since they both approach 52 on 3, this one has to approach it as well. So therefore, something like that. The law that I'm using here, the limit law I'm using, is literally called the squeeze law. If you've got two functions that both, three functions arranged with one of them between the other two, and the outside two go to a limit, then the minimum one has to as well. It's called the squeeze law. They used to teach it in Maths1A. Okay, so, but just pointing it out, if you ever go and look at upper and lower sums from other places in the world, they will probably mention the word squeeze law when they do this. There you go. That's the whole process. I will say that there was one other bit in the middle there we could have done differently, which I think is possibly slightly better, and I've only just thought of it, and I wish I'd thought of it years ago. If ln is this, if un was this, and ln was this, and we had this picture that I drew earlier, and that was where the ln is made of, and that's where the un was made of. If I subtract them, all the bits in the middle will cancel out. And so un minus ln will be left with just the one for, so un was this bit, wasn't it? And ln was this bit. The one for n minus the one for 0. And that's slightly quicker, because then you can just do equals and do the calculation of what the difference is, which is minus 64 on n, you know, dot, dot, dot. Well, plus 64 on n, I think. And so therefore ln is which is whatever it is. You know, that would be how the working works. So I like that working. That's kind of sweet. But just be careful. These will be the other way around if it's an increasing, if it's a decreasing function. So just be really careful about which one is part of the un and which one's part of the ln. So which one's left behind when you subtract them. Which is why it's kind of nice for me to draw the un as the outside box, because then it feels bigger. So we do the subtraction. Yeah. So you don't have to show this to the people who are reading your exam, but you can show it to yourself. So it's fine. All right, that took me longer than I had expected, but are we feeling okay about this process now? Yeah. So you could very quickly, if someone gave you a formula for ln or for un, you could figure out the other one if it was an increasing or decreasing function using this idea. This would be, if I were writing an exam, I would give people the formula for one and ask them to find the other, like as the exam question. I do not get to write the exams, which I'm very happy about, because it's not a fun thing to do, to write exams. You're never, it's like being the boss of a big company. You're never right about everything. Someone's going to complain. So I wouldn't like to be the person who writes the exam. That's upper and lower sums. So notice along the way in this that we did a lot of other stuff, right? There were bits here that were literally about what the meaning of the upper and lower sums is, where we figured out the maximums and minimums and things. But there was a bit here where we had to know what functions looked like and whether they were increasing or decreasing in order to do the problem. And there was a bit here where we had to do, there were several parts where we had to do sum notation manipulations and bits where we had to know a formula for a sum. And there was a bit where I had to do this sort of index shifting thing. Those sorts of moves are the things I really wanted you to have experience in while you're doing this course, because they are moves that if you do more courses, maths courses in the future, they will come up. Yeah. Okay. (1:30), right? That's when I'm supposed to finish. Yes. Okay. I'm just going to talk about this for a second, and then I will talk about subspaces, spans, and stuff. Inverse trig function calculus, since someone asked. Okay. Trig functions were invented several hundred years ago. We used to have 6 or 7 or 10 of them, but we now have 3. Well, technically 6. We've still got sec and cot and cosec, but we don't use them that often. Then when calculus were invented, it was one of the first things they did calculus on. Yeah. The inverse trig functions go the other way, right? So your trig functions, so a trig function takes an angle, and then you do a trig function, and it produces a number. That isn't an angle, it's just a length, right? And technically your angle is a length as well, it's just measured around the edge of a circle. So this is an angle around the edge of a circle. And this number is like a height or a length or a slope. Okay? That's what trig functions do. Your inverse trig functions go the other way. They take a number and they produce an angle. They go this way. Cool. Sweet. That's the general idea of them. The reason that people like to call them arc sine and arc cos and arc tan is because the answer for them is a length of arc. The word arc means part of a circle. For example, in French, the word for rainbow is arc-en-ciel, meaning arc in the sky. Yeah. Is that right? There you go. So that's why they're called arc things. But there is a problem in that, for example, sine of x, it will take any possible angle anywhere around this circle, even if you went around 27 times, and it will produce a number, which is this height here. So sine x takes an arc length, and it produces the height of the point above the x-axis. It produces the y-coordinate. And the problem is that there are lots of different angles that produce the same sign, and it technically doesn't have an inverse, because if you're saying, if you're going, so here we go, sine of pi on 6, oh, damn it. Is a half. So arc sine of a half. That's great, but sine of pi on 6 is a half, but so is sine of this angle and this angle and this angle and this angle and this angle. How does the calculator know which one to give me? Because it can only give me one. And it knows that it always gives me the one that fits inside a right angle triangle. sine of 5 pi on 6 is also a half. And arc sine of a half is still pi on 6, not 5 pi on 6. Yeah, it only produces the matching angle in the right-hand quadrants. Arc sine's range is these angles here. Is from minus pi on 2 to plus pi on 2. So no matter what angle you put into sine and you get an answer, if you do arc sine on that answer, you will only get the matching angle in these two quadrants. Yeah, worth noting. And arc cos's range so you have to pick. It has to work for the angles that fit in a right angle triangle, which are here. And you have to pick a zone along this circle that covers all of the possible answers for cos, which is this zone because cos is the x coordinate. If I went down here, that'd be this positive x's twice. So arc cos's range is from 0 to pi. And arc tan's range, tan is the slope of the line when you draw the point on the unit circle. That slope is what tan is. We have to have this, and we have to pick a zone which produces all the negative slopes as well, which is perfectly good to do that one. So it's the same as this. This is really important to remember, that arc sine and arc cos and arc tan only produce some of the angles. It is a strikingly wonderful coincidence, possibly not a coincidence, that the place where arc sine produces its answers is also the place where cos is positive. And the place where arc cos produces its answers is also the place where sine is positive. And the place where arc tan produces its answers is the place where sec is positive. The reason I said sec is involved in the trig identity that's got tan in it. And it's also involved in the derivative of tan. So this zone here is the range of arctan, and sec is positive here. And this is the range of arc sine, and cos is positive here. And this is the range of arc cos. Sorry, this was cos. Sorry, arc cos. And sine is positive here. And this is the range of arc sine, and cos is positive here. That is possibly a coincidence, but it is extremely convenient for calculating the derivatives of the inverse trig functions. So just to be absolutely clear, I'm going to give you the answers for what they are. If y is arc sine of x, then dy on dx is 1 over root 1 minus x squared. And if y is arc cos of x, what's that? No, that's definitely a minus. Then dy on dx is minus 1 on root 1 minus x squared. And if y is arc tan of x, then dy on dx is 1 on 1 plus x squared. The plus goes with the tan. And the tan doesn't have a square root. And in fact, look at this. The derivative of arc sine and the derivative of arc cos are almost identical except for the minus here, which is interesting, which is why most people don't actually use arc cos in their calculus very often, because it's the same as arc sine's derivative. So if you try to integrate this, most people would write it as minus arc sine and not arc cos. Just, you know, one of those things. If you ask Wolfram Alpha or other machine thing that does calculus, the integral of this will be minus arc sine. So we prefer sine over cos, or I don't know. Okay. These are the answers, but it is worth pointing out that you can prove that these are the answers. You are allowed to write this as cos inverse if you like, but just be aware that this is the one that a computer would have because it doesn't know how to do the power of -1. Desmos can do the power of -1, but it's just cleverer than that. Okay, so if you would like to prove that the derivative of arc cos x really is this, then you need to do some trig identity stuff along the way. So here is how I would do it if I were you. This is just how I would do it. I don't know. If I do cos on both sides of this, then it will produce this answer. And I know it's not necessary to write this next line, but it makes me feel better. And some people go direct from here to here, and that's fine too. Whatever works for you. And I can definitely figure out dx on dy. That's this. And dy on dx will be 1 over that, because I will pretend that dx on dy is an ordinary fraction. And so dy on dx will be the reciprocal of that fraction, and I'll get 1 on sine y, which is great, except that if I did dy on dx, I would expect my answer to be in terms of x. And 1 on sine y is not in terms of x. And I could sub in y equals arc cos x and get sine of arc cos x. Well, that's not the answer I'm going for. And also, what? So we're going to do some trig identity things. I know a trig identity that's got both sine and cos in it. And it goes like this. The fundamental trigonometric identity. And cos y is x. Thank you. And so sine y is 1 minus x squared. Except technically, if I'm going to do a square root, it could be either of them. A plus or a minus. Can't be both, because it's supposed to be a function. Are you ready? Ready? Look at this, look at this. If y is arc cos of x, that would mean that y is between 0 and pi. And sine is positive there. And so sine of y has to be the positive square root. But y is between 0 and pi. So sine y is positive. And so therefore sine y is in fact this one. And so therefore my dx on dy is minus root 1 minus x squared. And so dy on dx is, ta-da! What's that?
like do that through.
Yeah. Classic. Most times people come and tell me about the exam, maybe about a third of the time there's a proof like that in there. But again, I have no control over what's in the minds of the people who wrote your exam. Now, just going to say, the classic one that they give you in the lecture notes is the one for sine. But the same reasoning will work for tan and for cos. With tan, though, it won't be this trig identity. It'll be one with tan in it. So just while we're at it, let's just remember that trig identity. So you know that cos x or cos y or whatever it is that you're doing on, this is your trig identity. If you divide everything by cos squared, you'll get a 1 here. Sine squared on cos squared is tan squared. And 1 divided by cos is sec, so you'll get sec squared. So the trig identity that's got tan in it is this one. And that's why we end up with the 1 plus x squared when we do it. I'm just going to put thetas here just so it's a little easier to distinguish from what we were doing elsewhere. So that is your fundamental trig identity for tan, which you get from here by dividing by cos squared. Yeah. So I remember this one and then write that one down because there's no room in my head for both of them. Yeah. Out of interest, you can divide by sine squared and get the trig identity that's got cosec and cotan. What was that you were just saying? Yeah. I will say something else. It has not been impossible in past exams for lecturers to ask you to prove the derivative of the inverse of shine. You know what shine is? Hyperbolic trig sine. Yeah. Okay, so shine. We'll just move the h over here. Just want to point something out. You will do the exact same thing for a thing involving the anti-shine, but you will need to use a hyperbolic trig identity. And there is a good reason why I have written this trig identity with cos first. Because the hyperbolic trig identity, cosh plus shine, it's not a plus, it's a minus. But it's the wrong one if you put shine first. So I always write my ordinary trig identity with cos first, so that when I do the hyperbolic one, it's in the correct order. And luckily in English, it's in alphabetical order. Cos and sine. But, yeah. And but the dividing by cosh squared is still the same for arctan, for than as well. So there you go. That's that. Just wanted to point it out. It is technically possible to do hyperbolic trig substitution as well. I wouldn't expect them to put it in your exam. That would be extremely mean. But it's all the same. You just got trig identities with minuses in the other spots. I just want to add one thing here. The other trig identities that it is worth remembering or having written down somewhere if you can't remember them is that sine of 2 theta is 2 sine theta cos theta. And cos of 2 theta is cos squared minus sine squared. Yes, I mean, you can replace the cos squared with a 1 minus sine squared, and you can replace the sine squared with a 1 minus cos squared and get the other two versions of that. They are very important trig identities. The hyperbolic trig identities are that sine of 2t is 2 sine t cos t, exactly the same as the traditional one, and cos of 2t is cos t squared plus sine t squared. Yep. There you go. I don't know if you need to remember them. You probably don't for the exam, but I just wanted to point it out because this revision seminar is not going to be just used for people who are studying for an exam. There are people who maybe in the future, in their mid-semester, are going to go, what would David have to say about this? So, yeah. And maybe they'll be confused because at that point in the semester, they're going, what the hell is trig substitution? That's okay. It's fine. They'll be fine. So, yeah. Okay. And so final thing is the reason why you expect to use trigonometric substitution for things that have root 1 minus x squared in them is because the derivative of arcsine has that in it. That's one of the reasons that you expect that to help. Because officially, if you're going to go cos of u equals x, that's the same as saying u is arc cos of x. And so you're technically doing an inverse trig substitution technically. Yeah. This is one of my favorite facts in calculus. So anyway, time for some subspaces, hey? Wait, then we want to talk about any of the things I just said? Okay. Okay. I'm going to drink some water. Okay. Let's do this. All right. Okay. As I said before, at the time of recording the 2014 subspace span revision seminar for Maths1A is my second favorite revision seminar of all time. But to be fair, there's a certain amount of each semester's ones are my favorite because they're with the people that I'm with this semester. You're all nice people. It's nice to spend time with you. Thank you. So before we get onto this, it would be nice to have a bit of a brainstorm of things about subspace span, independence, that sort of thing. I'm going to give you 30 seconds to think for a bit about stuff that is about this. I recommend not looking it up at this time. Think what is in your mind about this general topic for a moment, and then we'll start saying some things. Anything. Yep. Okay, well, feel free to say anything. This is a brainstorm. There are no wrong answers. There are just what's on your mind. And the first thing that is on anyone's mind is coming from the Zoom, and it is, this is tricky. Okay, what's next? While you're getting ready, anyone want to say anything? I heard someone say the phrase linearly independent.
plus one.
Ah.
This was the question, and oh, sorry, this was the stuff from the video, and the question was, how do these two vectors span all of W? Just two vectors, but they're in like R4 or something. And I thought that to span something, it needed to be 4 vectors to span R4.
Cool. That is a very important thing that you've asked. Okay. Anything else you want to, that's on your mind? Just words, phrases, questions? Big theorem. There's one big theorem about matrices, right? Ah, yeah.
Different number of rows and columns, and there's another one that's the same row, same number of rows and the same number of columns.
Okay, cool. Yep, that's great. Very worthy point. Okay, this is an important thing to do every so often. If you are going to think about a topic, it's important to think about the things that you think about. Like, what is what's on your mind with that topic? What can you remember? What can you half remember so that you need to go look it up? It's a really important thing to do, to try to remember things so that you know what's missing. If you try and remember something and then you go look it up, your brain, it doesn't think this consciously, but your brain will go, oh, that was something I couldn't remember, and now I know. I will strengthen that memory connection. And now, even though you have a cheat sheet and you don't have to remember all the details, everything's faster if you can just remember it rather than look it up. It's much easier to solve problems you've never seen before if you can just remember stuff. So it's a good practice every so often to just try to remember. Okay. Okay. Let me just talk about some of these things. Got about 15 minutes. I might go another 15 minutes over the top of that. Feel free to leave at any time. I will not be offended. Okay. So, let me talk about what spanning is. The word span is both a verb and a noun. It is both an action and an object. And the people who run this course, apologies to any of you who may watch this video in the future, you have done your students a disservice. The first time they mention span to you, they set up in your mind a connection that is in your mind, based on that question you showed me, that is not helpful. So I'm going to start from a different spot. The act of spanning so just a second. So I don't know how to say this in maths notation, so I'm just going to say it. The action of spanning in linear algebra is finding all the linear combinations. That is the action of spanning. So if you have any number of vectors and you find all the linear combinations of those, that act is called spanning. And then the thing that you produce is called the span. Right. So if I say the span of the vectors 1, 0, 3, and -0.5, 2, 5, for example, this is being used as a noun. It is the result of the action of doing the action of spanning. And so this is a set. Oh, just give me a second. I may change my vectors, so just give me a moment. Make that a 4. I'm going to make that a 1. No, a 7. Okay. All right. Thank you for bearing with me. I just want to set something up for later. Okay. Okay. Right. It's a set of vectors that contains all of these things. So, for example, it contains 1 of this vector and 3 of this vector, and that answer, whatever that is, let's see, 1, so that's that vector is one of the vectors in that span, and it contains, -17 of this vector and 63/8 of this vector, and it contains none of this vector and 12 of this vector, and every possible combination that you could think of, and also the ones you can't think of, they're all in this span. Something times 104 and something times -0.5, 75 for all A and B in R. That is the definition. So this is what I'm thinking. These are examples. This is in fact equal to the set of this, given that A and B are in R. This span here is short for this. So the act of spanning is to take the vectors you've got and to find all the possible linear combinations, which means multiplying by scalars and adding them together in all the possible ways and coloring in all of those points. And the object that you have when you color them all in is the span of those two vectors. Okay. So let us imagine what that looks like. Didn't bring any Play-Doh. Just a second. This will do. There's one vector, and there's another vector, right? And the span of these two vectors would be, it includes this vector, it includes 2 of this vector, it includes 3 of this vector, it includes -6 of this vector, it includes this one plus this one, which ends up there. It includes this one minus half of that one, which is there, and includes -6 of this one plus 7 of that one, which is back here. And when you do that process, you can only produce vectors in this plane. And when I color in all of the things that I produce, I color in the entire plane. So just a plane, not the whole of R3. So the span of two vectors in R3 is a plane. This plane. Okay? So this object just here, this span of these vectors is a plane. It's a plane that is inside R3, but it isn't R3. And all of the points in this plane have three coordinates because they're points that are in three-dimensional space, and I need three coordinates to tell you where they are, but they are points in R3. Yep, I'm going to let that process and let you ask the question that's on your mind there. Yes, these two vectors cannot span R3 because there's not enough of them. I need three vectors to span R3. They span something. The thing they span is a plane. Now, I will say something very important here. Many people will go, oh, does that mean they span R2? And the answer is no. It's not R2 because the things in R2 only have two coordinates. And these points have three coordinates. It's the same shape as R2. It's just not R2. So the language you want to use, you want to call it R2. But don't, because officially R2 is things with two coordinates, and these things have three coordinates. So it is the only way to call it what you want it to be is to say it is a plane in R3. How do you feel about that? The Zoom meeting won't actually end in 5 minutes. I get to control that. So you can chill. It's okay. Okay. So if I did this, I have a vector with 5 coordinates. I do the span of that single vector. What shape is that? It's a line. Because if I was in R3 and I had one vector and I did all the multiples of that, it would be a line. It's still a line even though it's in R5. This is a line in R5. Yep.
So that just means the amount of linearly independent vectors will be the amount of dimensions this span, is it?
Yep, I'm going to repeat what you just said. The amount of linearly independent vectors is the amount of dimensions that the span has. Correct. We don't define the word dimension in Maths1A, but that is the exact definition of dimension in Maths1B. So this has one vector that makes a one-dimensional object, which is a line. Yep, the vectors have the same number of coordinates. Yeah, you can't add something with only 2 coordinates to something with 3 coordinates because there's a coordinate you can't add anything to. Like, so, okay, yeah, you could theoretically imply, I'm just going to pop that just here. You could imagine saying, oh, well, this would just be adding the first 2 coordinates. You could imagine that, but there's no particular reason why any one coordinate has to be more important than any other one. And so nobody knows which 2 of the coordinates you're supposed to be adding. So you just don't do that. But it is totally possible if someone said, if you did some geometry in R2 and you felt the need to extend it to R3 to say, I will now consider all my R2 vectors to have a new third coordinate, which is 0. That's an okay thing to do, but you have to explicitly say it. Yeah. Yeah. Good thinking, though. It is a thing that people do, but they have to be really careful about it. Yeah. Right. Okay. So we don't have names for when you get to a three-dimensional object. There isn't a name for that. Like a one-dimensional object is a line and a two-dimensional object is a plane. We don't have a word for three-dimensional objects. They're just called three-dimensional spaces. And in R5, there are lines, there are planes, there are 3D spaces, there are 4D spaces, and then there's everything. And so, cool. Right. They're not different to planes, they're just bigger. So it helps to this is one of the times where it helps to be aphantasic and to not be able to imagine pictures, which is how I am. And so you don't have to imagine what it looks like. You just have to know what it feels like. It feels like three space, it's just bigger. So there you go. And those of you who are now aware that aphantasia is a thing, about 10% of people cannot see pictures when they imagine. And you may be one of those people, and suddenly you realize that physically feeling like you can physically see a picture when you imagine is a real thing. So if I close my eyes and imagine things, there's just nothing there. So, yeah. There you go. But I can imagine what it feels like to be somewhere. And that's a different thing. So, now we know what span is. I will talk for just a few more minutes. It's okay to leave if you need to. Okay. So when we say that a set of vectors spans R3, what we mean is that when we do the act of spanning those vectors, the thing we produce is the entire of R3. Yep. You can't span R3 unless you have vectors with 3 components, but you also need at least 3 of the vectors to span the whole of R3. But even if you have 3 vectors, there's no guarantee that you will span R3. Also, yep. Because this vector is already a linear combination of these two, it's already covered in the combinations of those two. And so adding extra 7, 8, 9s doesn't add any extra vectors. So the linear combinations I can make from these two is the same as the linear combinations I can make from these 3. And it is because it's not 7, 8, 9. Wait. Thank you. It is actually a linear combination of the other two, though, is 7, 8, 9 anyway. Yep. I'm pretty sure, I could be wrong, but I'm almost certain that you can make 7, 8, 9. There you go. Two of this minus that. So because one of them is already a combination of the other two, that means that this is equal to the span of just 2 of them. The places I can get to using these 3 vectors is the same places I can get to just using these 2. I'm going to repeat that. That's because it's on the same plane that the other two already span. Yeah. This vector doesn't add anything extra because it's already in the plane that these two span. Right. So that thing of being inside the span of the other bits, one of them being a linear combination of the others, that idea is called being linearly dependent. So these three vectors are linearly dependent. So when your vectors are linearly dependent, they span less than you expect them to, because one of them's already spanned by the other two. Okay. Now, I just said the meaning of linearly dependent means that one of them is a combination of some of the others. But that's not the definition of linearly dependent. And the reason it's not the definition is because if you had to show that things were linearly independent, you would have to show that none of them is a linear combination of any of the others. And that's a lot of work. And just because you can't think of a combination that works doesn't mean there isn't one. And so we need a definition that is easy to check using procedures that we understand, such as row operations. And so the meaning of linearly dependent is one of them is a linear combination of some of the others. It doesn't matter how many it's a linear combination of. It's probably true that every one of them is a linear combination of all of the others, but just pointing it out. The definition of linearly dependent is on the next page. I feel like Osher Ginsberg saying it's after the break. Vectors V1 up to Vn, I will say K, are linearly dependent when x1 v1 up to xk vk equals the zero vector has more than one solution because we know it's got one solution. All the x's could be zero, but it has more than one. So in particular, it has at least one solution where the x's are not all zero. So you can say at least one solution where the xi's are not all zero. That's the definition of being linearly dependent. Now, in your notes, they don't have a definition for linearly dependent. Their definition for linearly dependent is being not linearly independent. So I'm just going to put that down here. Yeah. So the definition of being linearly independent is V1 up to Vk are linearly independent when x1 v1 up to xk vk equals the zero vector has only the solution that x1 is zero all the way up to xk is zero. And it's called the trivial solution. Trivial in ordinary English means not important. But in this is really important. It's just mostly zeros. It's the solution I would have thought of by myself. If I want to make the answer 0, I could just have 0 of all of them. And that's the one that I could have thought of without any training. So I'm going to say something. If someone says to you, are these vectors linearly independent? And you happen to notice that one of them is a combination of the others, you can just say this, therefore they're linearly dependent. That's perfectly acceptable as a reason why things are linearly dependent. But if you want to prove that things are linearly independent, you must use this. And in particular, this is something you can use in a proof, even if you don't know what the V1 up to Vk are, because it's an equation that you can rearrange using letters. This is the sort of thing you can only do if you actually know what the vectors are. And that's one of the differences. So one of the reasons that the definition has been chosen this way is because I can use it in a proof. Yeah. Right. Cool. So, sweet. So we have got two things going on. We've got spanning, which is an action you do on vectors to produce things like lines and planes. And we have linearly independent, which is when you span things and you don't get as much as you thought you would have expected. And we can ask whether a certain set of vectors spans a certain thing, or whether they span Rn, whether they span a particular plane. And we can ask whether a certain set of vectors is independent or not. Cool. So a subspace is guaranteed to be produced by spanning somehow. So the idea of what a subspace is, there is a definition, but the idea of what it is it is a thing that has been produced, pardon me, by spanning. What that means is that all subspaces are made by doing linear combinations. Yep.
Like the span of the vectors creates
A subspace, yep. So when I say like a subspace must be the span of some vectors. Now this is in fact a theorem, because the definition of subspace is not that it's the span of something. But this is why we care so much about them. Spanning is just what vectors do. Like the only reason we're allowed to call them vectors from a mathematician's point of view is because we can do scalar multiplication and addition. And if you're going to do scalar multiplication and addition, well, let's do all the scalar multiplication and addition, and ta-da, that's what spanning is. And so when you do spanning, those objects you make, lines and planes and stuff, those things, they're subspaces. And that's why subspaces must pass through the origin, because you can always do the linear combination, 0 of this and 0 of this and 0 of this and 0 of this, and produce the answer 0. Right. So a subspace must be the span of something, and the sum vectors that you use to span it, that is what a basis is. Is that what you just said? So if you're going to say, hey, here's my plane, which two vectors, because I know I can make planes out of two vectors by spanning, which two vectors can I span it with? The answer to that is a basis. That's what a basis is. It's the vectors that you can use to span your thing. So the question of find a basis for this subspace is actually saying, rewrite this subspace as the span of something and tell me what the something is. There is a technical detail. You can't just pick whatever you want here. You have to pick the shortest list you can of vectors to span it. Because that's not a basis, that is. Because these aren't independent. I don't need all three of them to span it. That's the basis there. Now, every plane has many, many possible bases. bases that you could have chosen. Many, infinitely many possible bases. If you're lucky, some of them will have whole numbers in their coordinates, but that's actually rare if you just think of random subspaces. Okay. I haven't defined what a subspace is, but knowing that they are spans, and spans are self-contained, like if you're in a span and you just do combinations of the things that are already there, you just do more combinations of combinations, and so it's just combinations and you can't escape. You can't escape a span by doing more spanning. And that's what the definition of a subspace is. You can't escape it by doing linear combinations. So that's the meaning of what a subspace is. It's a set of vectors you can't escape by doing linear combinations. It's full. And I'm really going to have to stop in just a second. And not being able to escape by doing linear combinations, I can just make that simpler. I can't escape it by multiplying by scalars. I can't escape it by adding. And it's got to have something in it. And it's definitely going to have zero vector. And so they're the three rules. The definition. Because you know when you do a linear combination of things and you use 0 for all of the scalars, the answer will be 0. And since you can't escape by doing linear combinations, you have to be able to produce the answer 0. W is a subspace when rule 0, the 0 vector is in W. Rule 1, if a vector is in W and you pick a scalar like a number, then K times W is in W here. That means you can't escape it by doing scalar multiplication, which technically covers this rule as well. But there has to be some vectors in it to begin with. You could technically describe some vectors and say, I've thought of the vectors where x squared plus y squared is -1. You go, there aren't any of those, David. So, okay, yeah, there has to be something in there. And 2, if U and V are both in W, then U plus V has to be in W as well. What this means is this means it's got at least one vector in it, and this means it can't escape it by doing linear combinations. And it turns out that the only things that do this are spans of something. And when you want to write it as a span, the list of vectors that you span is the basis. Yeah. That sort of thing. So this would be how you would be, if you didn't happen to notice what you noticed before, that this is 2 times this minus this. And you wanted to know whether these 3 vectors were linearly independent and wanted to know the size, the dimension of what they spanned, then you could do row operations to do that. And so I would do my new row 2 is the old row 2 minus 2 of row 1 to make a 0 in that spot. And my new row 3 is the old row 3 minus 3 of row 1 to make a 0 in that spot. It is okay to do both of these row operations at the same time because they are using the same row and using row 1 to affect 2 different rows. But please don't do row operations that change row 2 and then change it again at the same time. So that's the only time you're allowed to do 2 of the same one. So 2 minus 2 times 1 is 0. 5 minus 2 times 4 is 5 minus 8, which is -3. 8 minus 2 times 7 is -6, I think. 3 minus 3 times 1 is 0 because that was the point. 6 minus 3 times 4 is minus 6. And 9 minus 3 times 7 is 9 minus 21, which is minus 12. Okay. And I would like next, so when I do row operations, I try and make one column at a time. And I'm trying to get as much of the identity matrix as I can. And so I could, at the moment, I can see that this one's twice that one at this time. But if I really wanted to do it traditionally, I would say row 2 is minus a third of row 2 to get a 1 in that spot. And I do happen to notice I can divide by 6 here, so I might do that now. It's not necessary, but it makes me feel better. Again, I can do those two row operations at the same time because they affect different rows. And I'm not using one row to affect the other one. So now I'm here. And now I'm going to go row 3 is row 3 minus row 2. That'll put a 0 in this spot. And row 1 is row 1 minus 4 of row 2. That'll put a 0 in this spot. I didn't change row 2. This becomes 0. 4 minus 4 of 1 is 0. 7 minus 4 times 2 is -1. And here we are at this point. And what this tells me is that my 3 vectors are not linearly independent because there is a column that doesn't have a pivot in it. So there is a column 3 has no, the word pivot means one of these ones. No, don't need to do the augmented matrix. Yep. And so they are linearly dependent. But I just want to say something. You are technically trying to solve the problem of A times this plus B times this plus C times this equals 0. But since they're all zeros, there'll be zeros forever. And so you don't have to write them.
And you put them with that
Yeah. Yes, you put them in terms of columns, and also because the equations you're trying to solve, which is like A of this vector and B of this vector and C of this vector. If I have A of this vector and B of this vector and C of this vector, I'll get 1A plus 4B plus 7C equals 0. And that's a linear equation, and the coefficients end up in the rows. So put them as columns. It'll be safer. So that's linearly dependent because one of the columns doesn't have a pivot. And there is a row of zeros. And so they don't span R3. Now, the rows of zeros don't tell you whether they're independent. If your vectors have lots of coordinates, then you can have many rows of zeros before it stops being linearly independent. So this, for example, damn it. Yep. Those are still linearly dependent. No. You just look to see where the pivots are. But yeah, you're right though. Just point this out. If I only had these original 2 columns, I would still have made the same decisions for my row operations because they were based on these first 2 columns. And so if all I had was those first 2 columns, I would have ended up here and concluded they were independent. And so you can always pick out, if you've got a list of vectors, you can always pick out which ones are independent by row reducing and going, which ones produce pivots? And I'm going to go back to those, and those are my original independent vectors. Got a light bulb moment there. But if you produce a row of zeros, it means they don't span R whatever. So these are independent, but they don't span R5. But they will span something. It just won't be R5. To span the whole thing, you're allowed to have more columns. You're just not allowed to have more rows. Yeah, because you can always add as many extra vectors as you want, right? Like I can span R3 with 1, 0, 0 and 0, 1, 0 and 0, 0, 1, but I can also use 2, 7 minus 5 and 16 minus 27, 512 if I really wanted. So I can have as many columns as I want to span R3, but I need at least 3. That's right. So if you have too many columns, they become dependent. If you have not enough columns, they don't span R whatever, but they will span something. And so your original question was, how can 2 vectors span something in R4? Well, the thing in R4 they're spanning is only a plane. So they can span the plane, but they won't span all of R4. Okay, that's enough. Thank you, everybody.